Good afternoon to everyone. So this is the presentation on the water and wastewater treatment and conservation. And in the next slide, we will briefly tell you what are the things which we will be covering in this presentation. So we will be talking about what are the different type of water, and then the system and equipment, and briefly about the zero liquid discharge, which is now the order of the day. Then about water economics and norms fixed by the authorities. Then the liquid effluent discharge standard, water quality standards, and what is specifically quality required for power plant and cooling tower, automation and control, and some thumb rules for sizing the equipment. Now, this is basically, the objective of the this presentation is for sustained operation of a power plant or any plant, we require a good quality water, either as a makeup water or for the process water. Now, for this water, from that water, what is available with us, we will start treating the water to suit our requirement. While doing that, all efforts shall be made to use minimum amount of water, which means conservation of water, and also we should also use the effluent what is generated during the process, and also during the on the effluent generated in the plant, all should be taken to a recycling plant, and then we should use to the extent possible maximum quantity of this recycled water, which will reduce your raw water intake consumption or raw water intake from the natural sources. Then while doing all these things, some amount of discharge will be there. Even though we go for a zero liquid discharge, sometimes some of the effluent are getting discharged, so that we should strictly meet the requirement specified by the authorities. And when you do all these things, automatically there will be a commitment towards the environmental protection, which is paramount, and this will reduce your intake water. And the subsequent slides, what we will be talking is about what Holtec has done so far based on lots of study in different type of project and the research. And we will give various methods by which we have been doing different process for the different type of water. So we go to the next one. Now, if you see the different type of water for boiler makeup, especially boiler makeup, now you have borewell water is there, and the another type of water generally what you get is a river water, canal water, and mine water. Now, in case none of these things are available, then naturally, if the plant is closer to the sea, so you will get the sea water, and from there, whatever water quality required, we have to do the treatment. Now, in the case, these are all the general scheme. This is not absolutely this is the scheme. This is all the general scheme followed. If you go for a borewell water, where the TDS, total dissolved solids, is less than 150 ppm or milligram per liter, you will have a filtration system, that is a multigrade filter or a dual media filter, followed by strong acid cation, then the degasser. Degasser is used for removing carbon dioxide, and the strong base anion, and after that a polishing is done with a mixed bed. And this scheme will provide us the water which is suitable for our application, that is the makeup water, or sometimes we may also use it for the cooling water. Now, in case the dissolved solids are more, earlier, before RO came into the picture, now for all the water, only the normal DM plant were used. Now, in this case, if you see, if the TDS is greater than 150, it is preferable or it is more economical to go for a membrane-based separation system. Now, if you see this for a borewell water, where you have a TDS greater than 150, then we have to go for a filtration followed by reverse osmosis, degasser, and then strong acid cation and anion followed by mixed bed. This is one option which generally we follow in all the plant. The other option available is a filtration system followed by reverse osmosis system 1, then reverse osmosis system 2. That means the product water comes out of RO1 will go to the RO2 as a feed, and then it will be followed by electro deionization system, EDI. Now, in this case, the reason why we have to introduce the second stage reverse osmosis system, RO2, is mainly because EDA requires a very, very stringent inlet feed water requirement, especially conductivity and silica. If it is more, then we will get into the problem of the actual output what we want. So that is why generally when EDA is used, we will go for RO1 followed by RO2 and then followed by EDI. Now this is generally for the borewell water. Now where if you see the borewell water, it is assumed there will not be much suspended solids, much turbidity, and there will not be any colloids. Now here COD, BOD also will not be there. But again, for example, if you are taking a bore near some sewage canal or some canal, there is every chance that COD, BOD can come inside. And similarly, if the soil is very loose in a borewell, then the colloids can come inside. So these things, during the analysis of water, then based on the actual analysis, the realistic scheme will be decided. This is only general scheme what we have indicated. Then coming to the river water and canal water and mine water, these water are generally called surface water. It's a flowing water or a stagnant water. Now here also the same concept, less than 150, because it is a surface water and canal water, mine water, the water quality, especially the turbidity and suspended solids, will change from season to season. For example, during monsoon season, the turbidity can go up. Suspended solids can also go up. Colloids can also go up. So because of that, we have to have a clarification system as a pre-treatment to the filtration system. Now, generally we go for high rate solid contact clarifier, which is good for taking any fluctuation in the inlet turbidity. So that is why this clarification system followed by filtration system and followed by the normal cation and then a degasser, strong base anion, and then mixed bed. Now, because being a surface water, since colloids will be present, post-DM, that is post-DM, that is after mixed bed, we can go for an ultrafiltration system which will remove the colloids. The colloid, basically a colloidal silica, which is a chargeless particle which cannot be removed in a ionic removal. That is either cation, anion, or mixed bed cannot remove. So only the physical removal of colloidal particle will take place only when you go for a membrane type filtration system. That is why we are providing one filtration system, that is ultrafiltration system, after the DM plant. Now, since this ultrafiltration system is going to use reasonably pure water, so you can go for a tighter membrane, which means ultrafiltration system with a 10 kD membrane. That means 10 kilodalton membrane. That means it will remove even minutest colloid particle, and then you will get the makeup water exactly to the requirement of the process or makeup. Now, even in seawater, canal water, and mine water, there are cases, because in the upstream side, if there are some additions are there from the other industry waste and other things are coming, so there is every possibility that the TDS of the river water can also go high, and if it goes high, Then we have to go for the scheme will be similar. Clarifier, MGF. In this case, we have to introduce a reverse osmosis system. So ultrafiltration system will come as a pre-treatment for RO. Before RO, ultrafiltration will come, and then which will be followed by RO, degasser, other things remaining same. Now, the same as we saw for a bore well, here also the same thing will be there. Clarifier, multigrade filter, ultrafiltration, RO1, RO2, EDA can also be followed. So this is the basically the scheme for different type of water, generally what we use in our plant. Then the next one will be a typical scheme, which we will be showing you. So this is the typical water treatment scheme, which generally being followed with a DM after the normal DM, that is the MGF ACF ultrafiltration skid, and then we have an RO followed by degasser, SAC, SBA, MB. In this case, if you see, we have also introduced activated carbon filter. Now, it is a big debate whether to use activated carbon filter or not. In many of the plants, we have not used activated carbon filter. And in nowadays, some clients are willing to go in for an activated carbon filter. The main reason for not using activated carbon filter is activated carbon filter is prone for bacterial growth when it is not in use. Suppose you shut down the plant for 3 hours, 4 hours, there is every chance that the bacteria will grow, and then when we restart the plant, then this bacteria will go and foul the membrane. That means a biofouling can take place. So it is a question of in case ACF is used, it is a foolproof system for removing all the chlorine. Otherwise, if you don't want to go for activated carbon filter, we have to go for a dechlorination system, and that dechlorination system will take care of the requirement of ultrafiltration as well as the RO, because no amount of chlorine RO can withstand. Immediately the membranes will get oxidized, and then the next option is only to change the membrane. So that is why when the dechlorination system dosing is given, it is always an automatic dosing system based on the the value which we are measuring it. Oxidation reduction potential, ORP. We also call it as a ORP meter. There will be a set value for a particular type of water. It is basically an electrochemistry calculation for a particular type of water. ORP value will be fixed, and that will give a feedback to the dosing pump. So it will maintain the required ORP, which will ensure that no chlorine passes through passes into the either ultrafiltration or RO. Ultrafiltration can take some amount of chlorine, but RO cannot take any chlorine amount. And then this is, so that is the point which ACF, some people ask for it, but generally it is not required when we go for a good dechlorination system. Then finally, if you see that now all the waste which are getting collected in the neutralizing pit or a wastewater pit, now all the backwash from the regeneration waste from the DM plant, RO reject, UF reject, backwash of activated carbon, and the backwash of multigrade filter. Now, in addition to this, in a neutralizing pit, we will also bring the boiler blowdown, side stream filter backwash, cooling tower blowdown. So all the wastewater getting collected, and this will be further treated, which we will see in the next few slides. The next one is, this is another one, same scheme. Instead of DM, we go for RO1, RO2, followed by EDI. RO1, RO2 followed by EDI, and then that water is again taken to the DM water storage, and then further it will be used. Then we will go to the next one. Now we have come across two types. One is DM, another is a EDI for this. Now if you see the advantages of EDI, there are a lot of advantages are there in the EDI. If you see that operation, you will have manual, automatic, but EDI is fully automatic. Operation time, If you see, normally a DM plant will operate for 20 hours because you need minimum 4 hours for regeneration of the cation exchanger, anion exchanger, and mixed bed, and also filling up various the dosing tanks. Now, in the case, we have taken it as a 22 hours, but EDA is capable of operating 24 hours. Now, the advantage of operating 24 hours is your rate of flow will come down. Because of the rate of flow is coming down, because it operates on 24 hours, your pump size can be less, your pipe sizes can be less. So which will, on a overall cost of the plant, there could be some reduction in cost is possible when you go for a EDA and operate it for 24 hours. Now, degasser generally used for little pH boosting and also to remove the carbon dioxide. And then in this case, because we have RO1 and RO2, in the case of EDI, carbon dioxide can be removed by dosing sodium hydroxide after the RO1, and then which will be further removed in the RO2. So degasser is not required. We only need a small tank after the RO1 and use it as a feed tank for the RO2. Now, another advantage here is the degasser is actually open to atmosphere. It is an atmospheric tank, and also it takes the air from the atmosphere. So unless your degasser blower is the filters are all in a proper condition, there is every chance that you will suck all the dirt from the outside and then which can go into the tank itself, because then the air will go, water will come from the top, so there will be a flushing effect, so the dust will settle down in the tank. There is a possibility is there, but if the filters are good and proper maintenance is done, then this can be avoided. Now, in the case of DM, for regeneration of cation exchanger, anion exchanger, mixed bed, you require hydrochloric acid and sodium hydroxide. Now, in EDI, you don't need any chemical. And effluent generation and TDS will be very high in the case of DM. But in the case of EDA, there is no effluent generation because you don't use any other thing. Everything will come. Only some small reject will be there. In EDI, if 100% water is going in, the small reject which is coming from the EDI, which can be taken back into the RO1 or RO1 outlet tank. So this will also be not a wastewater. It will be again recycled back. Now, impact on environment. Now, fresh chemicals. See, the idea is when we talk about environment, in the case of DM, what you do is you take water and you add chemical by way of hydrochloric acid, sodium hydroxide, and then you make the water more environmentally not very friendly. But in the case of EDA, we don't use any external chemical, so there will not be any impact on the environment when you use EDI. Operation safety, if you see that, less due to chemical handling. You have a bulk chemical handling, you have HCl handling, NOH handling, but in the case, it is more safer in the case of EDI. Then the manpower for DM is high. In the case of EDI, it will be lower. Bulk chemical handling required, not required. Then space requirement is high in the case of the DM plant, and whereas in EDI, it is not that high. Operational skill, if you see, you require a little more better operational skill for the operator for the EDI because it's a high-tech item. And capacity enhancement. Suppose today you are having a DM plant of 10 meter cube and your upstream system is capable of adding some more as a feed to DM tank. Now, increasing the capacity of the existing DM plant will be little bit difficult and mostly it is impossible. But in the case of EDI, we can add modules. EDIs are like ultrafiltration RO, it is like a module. You can add one additional module, and then based on the excess available in the upstream side, we can still get the required makeup water quantity or a treated water quantity for the process. Now, considering the above, if you see, effort shall be made to go for EDI instead of a conventional DM. Because if you see most of the country in the world, they have gone only for EDI. Nowhere it is generally being used. Only now we are still using it. The reason is that some operational skill is required, which we have to develop so that it will become an operation of EDA will also like an operation of DM plant. We have to bring it to that level. So next. Now the other one is seawater. So we were talking now, if that water is not available, what do we do with this? So you have to take a seawater, and the seawater, if you see, it is a very high TDS water, varies from 30,000 ppm to 33,000 ppm, and depending upon the location of the sea. Now, Bay of Bengal will have one, and Arabian Sea will have one, and Indian Ocean will have one, and internationally, there will be a lot of difference will be there.
Rajan sir.
Yeah.
Sir, what about the EDI of pH value?
EDI of?
pH value.
No, EDA pH value will be lower only. After EDA, you have to go in for a pH correction.
Can we utilize for domestic purpose?
No, EDA generally, no, it is quite expensive compared to normal DM. So normally it is not used, and for domestic purpose, it is not required, because the reason is, if you go for a domestic purpose now, that means a household purpose, sir.
Yes, sir.
If you see, we even though we are telling you should not use an RO, you need some 100 to 120 ppm of salt. Otherwise, we will have a health problem. We cannot take a bland, or normal, distilled water. Distilled water is not suitable for human body. So that is why in a drinking water plant, if you see, after treatment, they will add. There is one process called a remineralization. They will add some remineralized, that salt will be added, which will be a food grade salt. They will add, and then only packing will be done. So normally 100 ppm of salt, especially calcium, is required, and it is good for heart also, calcium. So if you don't have, then you have to supplement it by other means.
Okay.
So that is why EDA is generally not preferred for any domestic application.
Okay, thank you.
Then coming to this,
I just 1 second. I just want to add here that we'll have a Q&A session at the end of this. So please keep your questions ready for that time. So we will take it at the end.
Yes.
Thank you.
Okay.
Yeah.
So that the total, apart from total dissolved solid, there will be a high amount of suspended solids, because it is sea. Everything will go to the sea. Turbidity will also be high. There will be colloid. There will be a lot of COD, BOD will be there. Now, normal scheme for the seawater will be, it is a seawater intake system. Seawater intake system is a very, very elaborate system, because you have to take at least a few meters or few kilometers inside from the sea, and then it has to be brought to the shore. So seawater intake system is by itself is a separate subject. It's a huge subject. There are many methods are there. Jetty type is there. Normal tunnel type is there. A pipe. You can also go for a piping type. Now, once the seawater is coming from the seawater intake pump, when it comes out, because when in the intake system, now you should also depend upon the fishermen, because all the filters and other thing, only those people will go and clean inside. They have to go underground, and then under the sea, and then clean all these things. Sometimes they also spray hypochlorite to remove all the algae and other things. Now, there is a stilling chamber. The stilling chamber is nothing but, which will reduce the velocity of the water. Then we go for instead of high rate solid contact, because the flow will be very high, quantity will be very high, we have to go for a lamella clarifier or a tube settler, followed by ultrafiltration, followed by RO. And normally any seawater desalination means we will reduce the TDS from 33,000 to 500 ppm. Now, after 500 ppm for our industrial use, you have to go for a similar treatment what we have talked for a borewell and surface water. The same thing will come there. Now, in the seawater, this thing, if you see, the recovery will not be high. In normal other water, fresh water application, you can go for a recovery of 70-75%. But in the case of seawater, no, it will be only 40 to 50% recovery you may get. Pressure required will be quite high in the case of seawater, because this is the pressure required. Normally in a reverse osmosis is you have to overcome the osmotic pressure. In a normal osmosis, the salt from the low concentration liquid will go into the high concentration liquid. That is called normal osmosis. A reverse osmosis is the other way. High concentrated liquid has to go to, and then it has to go to the low side. So that the pressure will be very high, somewhere around 60 to 70 kg, or even sometime it will be more. So it is a power intensive. Another thing what you can see is the feed pressure itself is 60 to 70. In that case, the reject pressure will be also somewhere around 60-65 kg per cm square. Now, what do we do with that high pressure, which is already we have spent power to increase the pressure of the water to some 60 to 70. So we have a reject pressure. Now, in the case of seawater desalination, we have to recover or use this pressure to increase the incoming water pressure. So that is why we have energy recovery devices there in the seawater system. That means whatever is going into these RO, seawater RO, some amount will pass through the energy recovery system, and then it will join the another line, and then both will together will go into the RO. So earlier days, the energy recovery is done by hydraulic turbine. You use small hydraulic turbine and use that, because seawater desalination, the capacities will be quite high. Even 1 MLD is quite high, 1000 meter cube per day. So you will use the hydro turbine, and that hydro turbine will be coupled with a motor, and then or with a pump directly, another RO high pressure pump, so that the power will be, that the pressure will be increased. Nowadays we have because the hydro turbine is again maintenance prone, so we have gone for a pressure exchanger. In the pressure exchanger, the RO reject will pass through the pressure exchanger. The feed water will come to the pressure exchanger, and when it's come out of the pressure exchanger, this pressure or reject pressure will get transferred to the feed pressure, and this will go into the RO system. So that is why the pressure and this pressure recovery is also an expensive product. Slowly, the prices will also start coming this. But nowadays, all seawater desalination plant, they go only with the pressure exchanger. Now, we have not talked much about the material of construction for the general water treatment plant, because most of you will know about it. But I just want to touch upon something on the seawater desalination. The low pressure intake pipe coming from the sea shall be generally be high density polyethylene. The reason is it will be floating on the seawater. So more flexibility is required. That is why people go for high density polyethylene, and which will take all the shock and other thing in the sea. Then once it comes into the shore, then you go for a low pressure application, the glass reinforced pipe. FRP is a generic term. Now here we call it as a GRP or GRE. That is glass reinforced plastic with vinyl ester resin, or glass reinforced epoxy, GRE with epoxy resin. Both are good. We can use any one. Because the vinyl ester is the better resin compared to the isotholic or a bisphenol resin. Then high pressure pipe. After the once it goes into the pump discharge, the pressure will be again 60-40 something, where we cannot use this either FRP or a HDPE. And the TDS is still not removed, because it is now only it is going to enter into the RO. So you have to go for a special pipe, which is called super duplex stainless steel or super duplex pipe. The idea, this is the number what S32550 or S32750. These are all UNI number of this American standard. And there is one thing which is, we should also check PREN number. The PREN number should be minimum, that is pitting resistance equivalent number, which you can calculate based on the composition of the seawater. And for the material based on the composition, you can calculate what is the PREN number, and it should be minimum 40. Earlier, people were using normal duplex steel, whose PREN number were less than 40. And then after some years of use, you get into the problem, because when a seawater desalination replacement and other thing will be time consuming. So for example, you are going in for a drinking water plant, you can't afford to stop anything. Huh? So we have to go for a super duplex steel, or now you have another one above that, super austenitic stainless steel is also there. All other piping after the RO product water, that is after desalination, the product water, which is a low pressure, you have to go for a stainless steel 316 or 316L to ASTM standard 312. Generally, 304 is not preferred. We have not used it in any of the normal water treatment plant or any of the seawater desalination plant, because of the molybdenum presence in the SS316 or 316L. In this 316 and 316L, 316L is more preferred, but it will be little expensive. 316 molybdenum is present, 1882 is the composition, so which will have better corrosion and pitting resistance. And you need a good disinfection system for a seawater, because you are taking it from the sea. All biological matter, everything will come. You have either a chlorination system or a chlorine dioxide system. Chlorine dioxide system is again an upgrade of chlorination system, and which is a fully automatic PLC or DCS operated system. In some plants it is used. In some plants still they go with a chlorination system, and the safety and other things we have to take care of it. Now this is a typical seawater scheme. Intake will come to a stilling chamber, then flash mixture, then followed by this lamella clarifier, clear water tank, then the filter feed pump. The filters, this is the multi-grade filter or a dual media filter. Generally, because the flow is very high, you will have a horizontal tank only. So from this tank, you go through the basket filter. Then you go to the ultrafiltration system. Then from the ultrafiltration system, the product water is stored in the last. There are two tanks are there. The ultra-filtered water is stored there. Then the continuation is next slide. You can see from the ultrafiltration system, through the pump, it goes to the micron cartridge filter, and it passes through the RO high pressure pump, RO, and then you have a suck back tank, which is provided after the RO, slightly in an elevated position. Then finally the permeate goes. Now if you see in this drawing, you can see a pressure exchanger. The RO reject which is coming, which goes into the pressure exchanger, and then the final reject comes out. And if you see the inlet to the RO, you have a feed line which goes into the pressure exchanger, and then whatever balance pressurization is required, that will be done by the booster pump. And finally, both the pumps discharge connects, and then it goes into the RO, and then finally treatment is completed and goes to this tank, this RO permeate tank. Now there is a suckback tank. Generally it is provided, it is at a higher elevation. If suddenly there is a trip, what will happen? You have to fill up the treated water into the RO membrane, because RO membrane cannot be kept with a high concentrated seawater, because in the seawater, which RO membrane, the seawater with 33,000 TDS goes, and finally it comes out at 500 TDS. So lot of TDS, the seawater, storing the seawater as inside the RO skid. will damage the membrane. So you have a suckback tank. By gravity, once if there is a high pressure pump or any pump trips, by gravity the water will come back, and then it will stop the RO water going into the, it will flush, as well as the capacity is calculated like it. First it will flush it, and then it will store it with the RO product water. So this is something, which normally we don't follow in our normal treatment. So this is about the typical scheme for a seawater desalination. Now, industrial wastewater and the treatment. Now, we have treated the water, normal water and seawater. Now, from that, we are getting a lot of waste. Now, industrial wastewater can be industry centric. If you go for a cement, power, pharma, generally you don't get, the oil, high COD, or then oil, this one, colloids and other thing will be there. The COD, BOD and oil and grease may not be very high. It will be present, but not very high. So that is the industrial. This water, you have to, you can treat it. And then the treatment, generally depends upon a freshwater treatment. Only thing is, in the clarifier, some additional dosing will be done. If at all any heavy metals and other things are present, or if the pH control has to be done, that will be done. So clarifier, MGF, UF, RO. So this is a treated water. Then if you go for a food and oil, gas, sugar, TDS will be high, and then the TSS, turbidity, and COD, BOD will be high. There is every chance, this one, oil and grease also will be there. Now, the moment you have a high oil and gas, then we have to go for a dissolved. After clarifier, you have to pass it through a DAF. DAF is nothing but a dissolved air flotation, where it will remove the oil and gas depending upon the quantity of oil and gas, the number of ppm of oil and grease. You may either go for a two-stage DAF or a single-stage DAF, followed by filtration, ultrafiltration, and RO. The further treatment, if you see this, the normal scheme, if you want to use this water for cooling tower, you don't need any other treatment. As it is, the RO permeate can be used. If you want to use this water as for a boiler makeup, then after RO, post RO, you have to go for either DM, or you have to followed by a DM followed by EDI. So that has to be same as what we have seen in the earlier. Now coming to the next one, this will be the scheme. If you see the same scheme, but RO permeate water is stored in a tank. After that, we can take as it is to the deaerator, or the RO permeate water can be taken directly to the freshwater degasser. That is, a freshwater degasser is shown, and then this scheme will, the other water treatment scheme will remain same. So you get a DM water storage. It can take into the DM water storage, and then further it can go to the various uses. Now coming to the other one, sewage water and the treatment. Now in the sewage water, we will differentiate as a sullage water and sewage water. Sullage water is basically a kitchen waste, bath waste. And sewage water is basically the waste from the toilet. So if you see the normal constituents, we have very clearly indicated TDS will be high, TSS will be high, turbidity will be high, everything will be high. So here you have to go for a treatment scheme will be, a bar screen will be there, settling tank will be there, DAF will be there, then followed by biological. Because of the very high COD, BOD, oil, grease, biological treatment is required. Then after the biological treatment, if you want to dispose it off, you have to go for a filtration system followed by ultraviolet system. Then you can dispose it off. Now further treatment, suppose you want to use it, either sewage water, sullage water also to be used. Because for example, in some of the major cities, the big industry will get only the secondary treated sewage water as a raw water. They don't get any fresh water. They don't get any seawater. They only get secondary treated sewage water as a raw water, as a water for the plant. Now they have to treat from the secondary treated sewage water to suit for boiler application, to suit for cooling tower application, to suit for any other process application. So any further treatment, if you want to go for it, then it has to be followed by MBR, MBBR, followed by RO if wastewater is to be used. And sewage water, the scheme is same, exactly same as what we have given. Now, MBR is nothing but an ultrafiltration system. MBBR is the moving bed bioreactor. This MBR performance is consistent and very good compared to MBBR, but MBR will be costlier, and this will be not like an ultrafiltration system of the freshwater treatment. This will be a submersible type cassette type membranes. It is not a circular module. This circular type. It is a cassette type submersible membrane where the sewage water or a sullage water will get sucked through the pump in the downstream side of the membrane, and that is the difference in MBR and normal ultrafiltration. Next. Now, this is a normal scheme which generally we follow. Crude effluent, that is which requiring a biological treatment. You see collection tank, then rotary drum screen, and balance tank, then DAF, pipe flocculate. That is the pipe, because then DAF also, no, you have to do some amount of coagulation and other thing before it gets removed. So pipe flocculator is there, where you add acid and alkali, and then polyelectrolyte is also is added. Then dissolved air flotation, depending upon the amount of oil and gas. Sometimes you go for one single stage DAF, in other case 2-stage DAF. Then finally it comes to the biological treatment, where you go to the aeration tank 1, then aeration tank 2, and here also anoxic tank will also be there. Sometimes the anoxic tank will be there, because the biological tank, which includes anoxic tank followed by aeration tank, then it go to the sedimentation tank, which is again nothing but some sort of a clarifier. And then the clear water is taken to the tank, followed by dual media filter, activated carbon filter, ultrafiltration system, and then it goes to the treated water tank. Now, from here, the decision is by the owner of the plant, whether you want to dispose it off or whether you want to reuse it, and all those things. Now, the sludge which are collected from this will go to the sludge holding tank, and then the centrifuge will be there. From the centrifuge, the solid which comes out of the centrifuge, which will be more or less a solid, and disposal will be easy, or you can take it to the drying pit, and then for landfilling can also be used. For the next one will be for a sewage. Sewage is identical. There is no change. Now, system and equipment. What are the system? For pre-treatment, you have to go for aeration. Some water require aeration. If the iron is very high, manganese is high, and some H2S water is there, you have to go for a aeration type. Aeration can be a cascade type or a gravity type, and then which is a spray or a fountain aerators. Then diffused aerators are also there. It removes all these things. Undesirable gas like H2S, reduces odor, iron and manganese. And this is aeration is one of the best treatment method. Especially the cascade aerator. Without any power, we will remove, I think, most of the iron, because RO system or water treatment system cannot handle iron. Then coming to the clarification, you have different types of clarifier. High rate solid contact. Now, high rate solid contact clarifier, which can handle a fluctuation in the turbidity level. We can always decide what should be the speed of the propeller shaft, and how much ppm of chemicals have to be dosed. All those things can be done. So normally, that will be done by there is a jar testing kit will be there. With that, they will do that. Then lamella clarifier, and then there is an active flow high rate compact clarification developed by Veolia water technologies. Then here also it is same, suspended solids. With outlet TSS less than 20 ppm, turbidity can come down to 20. And then in the clarification system, some heavy metals can be removed. Some amount of hardness can also be removed. Then go to the filtration system. This is normally a multigrade filter or a dual media filter, an activated carbon filter. So again, the outlet, this is similar to our normal water treatment plant. Outlet TSS will be 5, turbidity will be 5. Activated carbon filter removes color, odor, chlorine, everything it removes. So activated carbon filter is definitely, it should be a part of the drinking water plant, but for industrial use, we may not use it. Then oil gas removal, you have a dissolved water flotation or a walnut filter. Walnut filter is nothing but our normal walnut, the dry fruit. That shell will be used as a medium to remove the oil and grease. In fact, in Holtec, we have used in 1 or 2 projects walnut filter where there is a high amount of oil to be removed before taking it to the water treatment plant. Then the membrane-based system. If you see, there are 4 types are there. One is the microfiltration, another is the ultrafiltration, then nanofiltration, finally comes to the reverse osmosis. Now, microfiltration, ultrafiltration, both are fully automatic and both are hollow fiber membrane made of normally polysulfone or polyether sulfone or PVDF, which removes turbidity, colloids, maintains silt density index, which is a number which has to be maintained by about 3, which is recommended by the RO membrane manufacturer for a prolonged life of the RO membranes. And ultrafiltration, it also removes the virus. In fact, in all Western countries, in a drinking water plant, ultrafiltration is a must. Chlorination does not remove 100% virus. Only the ultrafiltration removes virus. There are some studies are also there. Then, so these 2 filtration, micro and ultrafiltration, will remove only the suspended impurities like turbidity, solids and other things. It doesn't remove any ionic salt. Dissolved salt doesn't remove. Then coming to the 3rd and 4th, one is a nanofiltration after the ultrafiltration. And then this removes some amount of, this is also fully automatic or a semi-automatic plant. This also remove some amount of ionic load. Generally, diatomic salt can be removed. That means calcium and magnesium can be removed in a nanofiltration. So nanofiltration is, in other words, can be used for softening. The general softener, what we are using in all the industry, I think we should dispense with that, because that is one of the major system which pollute the entire area. Because you add lots of salt and then the waste which is coming out of the softener, it will have huge chloride content, and which will damage even the earth also, the groundwater also. So nanofiltration is in between ultra and RO, which remove the diatomic salt, which can be used with that. It can remove calcium and magnesium. And then coming to the reverse osmosis, which is an ultimate, where it removes theoretically, it removes 98% of the salt with a 2% of slippage of salt in the product water or a permeate water. And this is a general this thing. If you see this macro particle, which can be seen in a visible naked eye, then some micro and then molecular range optical microscope, then electron microscope. And if you see that, in the bottom you can see, first is a particle filtration, is normal filtration system, microfiltration, after that ultrafiltration, then nanofiltration, reverse osmosis. Reverse osmosis will remove the ionic up to 1 Armstrong. That means 0.0001 micron. Up to that it will remove. Now, post RO treatment following configuration, which we have already seen. So some slippages are coming from the RO plant, which has to be removed in the DM plant, SAC, SBA. So SAC will remove the sodium slippage up to 1 ppm, and the silica in the SBA will be the silica slippage up to 0.3 ppm. Even that, this is not sufficient for a boiler makeup or some pharma company or even for semiconductor industry. Nothing, this is not sufficient. So you have to go for a polishing unit. The mixed bed is nothing but a polishing unit, which will have both cation resin as well as anion resin. So it removes the residual cation and anion which is coming out of the RO plant to the required level of 0.2 microsiemens per centimeter, the conductivity, and silica less than 0.02. That means, and then iron less than 0.01, sodium, potassium put together less than 0.01. This is what is required for our boiler application, and semiconductor. In semiconductor is still more stringent. Pharma also like that. So either instead of 1 and 2, you can straight away go for an EDA. EDA is nothing but combination of membrane and resin. Both are there. So after second stage RO, you can use this and get the required water quality for our process and other application. Now, water economics norms. What Central Pollution Control Board has fixed. This is only a brief, only for few industry we are talking. Power plant 3 meter cube per megawatt hour is the limit of freshwater intake, beyond which you are not allowed to take. And for power plant, compulsorily you have to go for a zero liquid discharge. In the case of sugar plant, you can discharge only 100 liters of water outside the plant per ton of cane crushed. In a cement plant, it is very clearly indicated that all efforts shall be made to go for a ZLD, zero liquid discharge. But they have not told compulsorily like a power plant, but this sentence is there. All efforts shall be made to go for a ZLD so that no liquid will be discharged outside the plant. So 95 to 97% of the wastewater have to be reused. Now, if you want to go for a good economical usage of water, and treated sewage water can also be reused. As I told you, either it can be discharged or it can be used. Discharge means it can be used for gardening and other things. See, incidentally, nowadays what people are doing is the sewage water is a kitchen waste, kitchen and bath wash. That is a cloth washing. Sewage is a toilet. What generally in a big mall, big apartments where hundreds of houses are there, or big factory, what they do is they treat the sewage water, and that the treated sewage water will be used for the flushing purpose or for bathroom purpose. They will not take any fresh water for bathroom, for toilet. They will use only the treated sewage water. So in the initial stage itself, planning has to be done, plumbing has to be different, and then the disposal has to be different. So in many cases, it is being done. Now, this is the general standard given by the Central Pollution Control Board. Many things you can see here, everything is present in the document. The only thing, the TDS 2100 ppm is not very explicitly told that whatever you are going to dispose, the TDS shall not be more than 2100 ppm. The reason why originally it was there. Now, I think now they have removed it. The reason is, in some places, even the borewell water, when you take it out, it will be more than 2100. So then the people started asking, no, my groundwater itself is more than this. Where will now? How can I get? No, I have to dispose it off if it is not required. So, but wherever it is lower than the 2100, the Pollution Control Board, if they come for an inspection, they will insist on 2100. But where it is not possible, they are not very this thing. Then coming to this is the STP plant. This is again the same thing. And you see here that there is a note in the Central Pollution Control Board. Stormwater is not allowed to be mixed with the effluent, treated sewage water, scrubber water, floor wash water. Okay. Stormwater shall be channelized through a separate drain. This is nothing but an indirect way of rainwater harvesting. So then that water can be taken to some sort of a storage, and then we can use the rainwater for further treatment, which will further our cause of economics in water usage. This is the standard which are available. Feed water, the IS standard, feed water and drum water, IS 1049 for high pressure boiler and low pressure boiler, drinking water standard, and cooling water makeup also some standards are given. But the main issue, apart from IS, there are other European norm, EN standard is there, American norms are there, individual turbine manufacturer, they also give some standard for their turbine that my turbine can take only this much. So these are all general guideline for referring the standard. Boiler makeup water quality, if you see this, whatever we have discussed, the most important is the conductivity and the silica. That is the total silica, which is the addition of reactive silica and colloidal silica. That should be less than 0.02 ppm. It cannot be more. Higher the silica means that every chance that the silica salt will deposit in the turbine at the low pressure at the end of the condensing side, and silica scaling cannot be removed by normal flushing or washing. It has to be shot blasted. Once you do the shot blasting, for that means it's a big process. You have to take the rotor out and then do the shot blast, because sandblasting is banned in India. Only shot blasting has to be done. So shot blasting has to be done. The moment you do the shot blasting, the surface finish of the blade will go off. It will become rough. So even though you will run the plant, but with a lower efficiency. So we should ensure that the silica is very, very, that is why in our plant, we always give online silica analyzer, some 2 channel, T-channel. And also we always tell the user that at every location, the guarantee parameter, what is being specified, has to be maintained. Unless every individual parameter guarantee is maintained, you will not get the same guarantee what you want at the outlet of the plant. So that we are also telling. So this is what is required. And then if you go for pharma and if you go for semiconductor industry, it will be still more stringent. Another important thing is, apart from silica, the turbine problem is the copper. Copper is another very, very important thing. The copper also goes and deposit in the turbine blade. Now, generally, there are n number of articles available in the market or in publications. Now, copper is termed as copper is a thief. That means once the copper gets deposited, then your generation efficiency or your everything will come down. So then from where copper will go, means the copper will go in case of a water-cooled condenser where you use Admiralty brass as a tube. Then there is a possibility of copper deposits will be there. So that is also one of the important parameters to be maintained. This is a cooling tower circulating water valve. This is not the makeup water. The cooling tower can permit a TDS of 4000, hardness of this much, alkalinity, calcium. So many things. Now, depending upon the cycles of concentration, your makeup water has to be decided. Suppose I want to operate with 6 cycles of concentration, my makeup water will be all these value divided by 6. If I want to operate with 4 cycles of concentration, then I will go divided by 6. Now, so depending upon the cycles of concentration, the makeup water quality will vary. So normally, as a guideline or a rule, 4 cycles of concentration is used, because if you see the cycles of concentration and the makeup water curve, after 4 cycles of concentration, the reduction in makeup water quantity is not appreciable. It is actually, the curve is directly, it will be flat. It will start from the top with 1 cycle and then it will drastically come to 4 cycles, very less makeup water. After that, 5, 6, 7, 8 COC, it will be more or less flat. But what will happen is, the higher the cycles of concentration, if you use a better water for cooling, higher the cycles of concentration means you will reduce some amount of chemicals which are used for the cooling tower. Then automation and control for water treatment. So this is a general, normally we follow. Clarifier will be generally manual. MGF AC operation manual or can be automated. Automatic operation, all the frontal valve will be pneumatic. But generally, in Indian condition, manual operation is preferred. UF is fully automatic. You can't operate manually either by PLC or DCS. RO can be fully automatic or semi-automatic. Semi-automatic means tripping is automatic, restarting is manual. That is called semi-automatic. Fully automatic means tripping and restarting automatic. DM plant also same thing, manually and automatic. Automatic operation of DM plant and all frontal piping valves shall be pneumatic operated. Then preferably all dosing system. Now, especially the RO feed, HCl dosing, SMBS dosing shall be automatic. pH correction also should be automatic based on the pH measurement. In cooling tower, sulfuric acid dosing has to be automatic based on the pH measurement. STP can be manually operated or auto operated. Plants will PLC or DCS of the WTP will be locally operated and will be hooked up with the plant DCS system, because you will not operate the WTP from the the total, the CCR building. You will have a local operating station will be there. You operate, but there will be a cable which is connecting to the CCR building operating system, where from there you can assess the condition of the plant, how the plant is running and what are all the parameters. Now, effort shall be made to go in for a fully automatic plant for getting consistent quality of water and also to take instant corrective action. This is more important. Now, in automatic system with a proper instrumentation, high level of instrumentation, instant corrective action is possible to avoid major breakdowns. And all dosing system also in that case, all dosing system will also be automatic. Now, this is a general sizing criteria for equipment and piping. This is all thumb rule only. The guidelines given in various reference book and then handbooks. Clarifier, the rise rate. Rise rate is 1.8 meter per hour. Retention time should be 2 hours and 30 minutes. Lamella clarifier and tube settler, rise rate will be 1.2 meter per second. Then the surface velocity of the MGF. That means MGF diameter and DMF diameter has to be sized based on 11 meter per hour. That means 11 meter cube per meter square per hour. That is called the surface velocity. And then blower has to be sized with the 55 meter per hour blower capacity. ACF surface velocity can be little higher, 15, and side stream filter surface velocity can also be little higher, around 18 meter per hour. And UF, now in UF also now we have to be extremely careful. Gross permeate, there is a two terminology we use in the UF. One is a gross permeate, another is a net permeate. Net permeate is the water which is required for the RO feed. But if you size like that, then we will get into the problem of water shortage. Because the reason is RO is continuous operation for 20 hours, 22 hours, 24 hours. But ultrafiltration in every hour, it will not operate for at least 5 to 7 minutes due to backwash, due to flushing, due to chemically enhanced backwash. Now, every hour, if you see, there will be around 5 minutes totally. There will be either, depending upon the water quality, there will be two backwash or 3 backwash. The cycle will be there. So during the backwash time and during the flushing time, during the chemically enhanced backwash time, the RO will not, the UF will not produce any water. So when RO operates for 60 minutes, the UF will operate only for, let us assume 53, 54 minutes or the maximum 55 minutes. So you have to take care of that loss of time in increasing the flow. The another one in the ultrafiltration is you need some water for flushing. After chemically enhanced backwash, you require water to flush it and remove all the chemicals out, because otherwise the chemical will go into the RO system. So that is the reason why the thumb rule, there are scientific calculations are available how to calculate what should be the gross permeate, which we do in Holtec. But as a thumb rule for a normal people, thumb rule, it should be 25% more than the net permeate. And these are all the flux rate to decide the number of membranes required. Number of modules of ultrafiltration. Forward means the actual production time, production cycle, 75. Backwash will be much higher flux rate because it has to remove all the dirt which are getting clogged to the membranes, hollow fiber membrane. Then CIP flux rate is the clean in place flux rate. Clean in place means sometimes you have to go, in spite of backwash, in spite of chemically enhanced backwash, if your UF is not coming back to the original form, then you have to go for a clean in place flux rate where you have to use some chemical, either acid, alkali, whatever it is required depending upon the fouling. You have to do this. That flux rate should be 140 LMH. That means liter per meter, that is a liter per meter per hour. Meter square per hour. Sorry, liter per meter square per hour. LMH is the expansion. Then RO high pressure pump selection shall be for, in Indian condition, it should be for a 25 degree, because the lower the temperature, higher the TDS, RO high pressure pump pressure required is much higher. And even though the flux rate allowed, normally, which is allowed for, say, 27, 28 LMH, Generally, for a conservative design, you go with a 20 LMH. And CIP capacity is 9 meter cube per pressure tube. Because array-wise cleaning will be there. In the first array, if there are 3 pressure tubes are there, the CIP pump capacity will be 3 into 9, 27 meter cube. And the pressure tube design will be ASME section 10. We need not go for a ASME stamp, but we should always tell the supplier of the pressure tube that it should be designed as per ASME section 10. So degas are surface velocity, SAC, SBA. So these surface velocity dictate what should be the diameter of the vessel. So for that only, these are all thumb rule only. It can go upward or lower depending upon the type of system what we are going to follow. The next will be allowable piping velocity. The pump for the pump suction below NB50 velocity is given. Normally, lower the pipe size, lower the velocity. 50 to 150 is given, and 200 and above it is given. It's at the maximum you can go for 1.2. And similarly, pump discharge, water pump discharge, it is 0.9 to 1. 50 to 150 is 1.2 to 2, and 200 and above we can go to up to maximum of 2. That means when I say range 1.5 to 2.2, 1.5 shall be used for the lower pipe size. That can be 200, 250. And if it is, say, let us say 300, 350, you can go for 2.2. Then these are all the velocity generally recommended for the hydrochloric acid, caustic soda, sulfuric acid, and sodium hypochlorite. In this case, if you see sulfuric acid, you have to be extremely careful because of the crevice corrosion and then pitting. So you should not exceed the velocity beyond 0.5 meter per second, all other 1 meter per second. So this is the last one. Thank you very much.